Okay, let's say we have a problem where we have this loop-de-loop here shown, and there's some cart which is moving forward this way, and then it passes to the lowest point B. From A, here's where it is at A, and then passes forward to this point B. And once it hits point B, it's in this circular motion around this circular loop-de-loop, right? And this is a frictionless surface, let's say, and we launch this thing forward at a velocity of 44 meters per second, like that, 44. And we are given the radius of the loop-de-loop. It is 15 meters. So let me try this again. The radius of our loop-de-loop is 15 meters, or 15 meters. And of course that's a constant radius, it's the same radius everywhere. So no matter where you draw that radius, it's 15 meters. The mass of the cart is 55 kilograms, let's say. And what we have to find is the force of the loop-de-loop, the force of the track, right, this track. How much force, how big is the force of the track on the cart at point A and at point B? In other words, find the normal force at A and at B. Excuse me, no. We will find the normal force at point B and at point C. There, like that. We're going to find the normal force at B and C. Now, this is a frictionless surface, so we're going to use circular motion to find the normal force at point B. We know that the sum of the forces is equal to mv squared over r, and at point B, the block has technically started its circular loop, so it's in circular motion at B, and the equation applies. Now, the velocity at A is 44, and since this is a frictionless flat horizontal surface, from A to B, the block travels forward, and nothing slows it down. So it still has all of its velocity at point B, and that means we can plug in 55 for mass, and we can plug in 44 as the velocity at B, and the radius is 15. So that's what we do on the right side of the equation. We do something else on the left side. Right? So this is a very active equation. Lots of things happening to this in this equation. Here's my free body diagram, and I'm going to draw a free body diagram so that I know what the net force is on my cart. So here's my free body diagram. Weight pulls down, gravity pulls down, and the normal force pushes up because the normal force is the force of the surface pressing perpendicularly against the object. Now, because my cart here is moving in a circle, it has a centripetal force. And what that means is that the net force, the sum of the forces, always points in toward the center. So if the block is here, then the net force, the sum of the forces, points toward the center. No matter where the block is, it always has this net force pointing in toward the center of the circle. So here's the center, so the net force always points in no matter where the cart goes. Which means that down at point B, there's an upward net force, and the only way we can have an upward net force is if the normal force is bigger than gravity. If gravity were bigger, we would have a downward net force, and that's clearly not the case at point B, since we're moving in a circle. So the net force then is equal to the normal force minus mg, and that gives us a positive number, right? Since normal force is bigger, and having a positive number as the sum of the forces is important, because in this equation you're only allowed to plug in positive values for the sum of the forces. Okay, so I plugged that in for the sum of the force, and of course we know that I'm plugging something in which is positive, so I'm obeying the golden rule of this equation, which is you have to plug a positive number in for or a positive equation in for sum of the force. All right, now, the normal force then is 55 times 44 squared over 15 plus, I'm adding mg to both sides, that's 55 times 9.81. And what do we get as our answer when we plug this into the calculator? We get the normal force at point B being equal to 7,638 newtons. Okay, now we're going to find the normal force at point C. So at point C, yes, let's see. Are we moving in a circle at point C? Of course we're moving in a circle. We're on this circular loop-de-loop track. And so this is just the funny name that we give for the circular track, like in a roller coaster. We call it a loop-de-loop. And if we are moving in a circle, then we know the equation for circular motion holds true. And let me make this a bigger, better V. And of course, this is the velocity at point C. So I'm going to call it V sub C. And on the left side, I need a new free body diagram so that I can figure out what the net force is on my object. So I'm going to take away my old diagram. And of course, when I draw my free body diagram, I'm going to remember that I'm only allowed to plug in a positive value for sigma f. Okay, for my, oh gosh, at point C, we are against the track, but we're upside down, so the track is here. And of course, gravity pulls down, but the normal force is also pushing down, because the normal force always presses perpendicular to the surface itself. So if the surface is like this, then it's pressing down, right? So F net then, or sigma f, if we prefer that, sigma f is, well, we have to plug in a positive value for the sum of the forces. So even though we normally would say that this is negative mg minus fn, we're just going to make everything positive. We're going to say down is the positive direction, which means the sum of the forces is mg plus fn. So we've assigned down the positive direction since we have to make sure F net is positive, the sum of the forces. So we plug in exactly that, right, over R. And then we look at this equation. Do we know mass? Yes. We know G. We're trying to solve for Fn. We know mass. We know R, it's 15. But we don't know the velocity at C. So before we can solve for the normal force, we have to find it. And we're going to find it using we're going to find it using conservation of mechanical energy. So here we go. Find the velocity at point C. And I'm going to do it in blue. We will compare the mechanical energy at point A to the mechanical energy at point C. And of course, mechanical energy is conserved in the absence of friction. So whatever mechanical energy we have at moment B is the same as what we have at C. I'm going to call the ground my zero level. And that means that at moment B, right here, the block is moving forward. So it has kinetic, but it's not elevated above my zero level. There's no height, which means that the block has no gravitational potential energy. Now the block, or it's not really a block, it's a cart. The cart comes swinging around this track, the loop-de-loop, and at point C, it still is moving, so it still has kinetic energy. But it also has gravitational potential energy because it's now elevated at some height above my 0 level. Here's the 0 level, and this is the height of the cart at point C. So it has MGH, like that. Okay, so to solve, well, first thing we see, just by inspection, we notice that the masses cancel, so you don't need to plug any mass value in when you solve. And what I have is 1/2 of the velocity at b, which is 44, squared, equals 1/2 of my unknown vc squared, plus 9.8 times, well, the height at point C is this. From here to here is 1 radius, that's 15 meters. From here to here is 1 radius, that's 15 meters. So the total height at point C is 30 meters. Whoa. And we get that, again, because we took the radius. We said from here to here is 15, from here to here is 15, add it all together to get 30 as the height. So we are going to multiply by 30. And you solve for VC in this equation, and what you get is 6.7 meters per second. So I'm going to erase my work here, and I'm just going to keep this here so that I can plug it in to my centripetal force equation. Okay, then here we are. I took that away, and I can plug in mass times 9.8 plus the unknown, the normal force, that's Fn right there. Try it again. Is equal to 55 times Vc squared, that's the 36.7 that I found. And we divide this all by the radius, right? The radius of the circular path, which is 15, not 30. 30 is only the height. The radius is 15. The diameter is 30. But we do the radius here, and you solve for Fn, and what you get for Fn is, let's see, 4404 newtons. And that's how you solve.